I'm loading. Okay, I'm loading. I've got some soft sediment deformation. I come up into a bed. Ignore the swirls because those are soft swirls. Okay, so I have a loaded bed. This is fairly massive and very thin up here. You can start to see a TB bed. Plain parallel laminations, which is bound with TB. And then, of course, you get another kind of a ripple or flame structure because you're loading. This is in a very soft sediment environment. Characteristically, this is just a shale bed. And then, of course, here's another foundry. Here's a small clastic conglomerate at the base of this TA bed. And then you can start to see plain parallel lamination and then very delicate TC ripples starting to, so TA, TB, or TA, TB, and see that climbing ripple right there? TC. TD is commonly absent, so that would be TE. So that's a Bauma bed. That's a shelf turbidite, a storm bed. So something swirled something out up here and it went shoosh off as a fluidized flow, and it froze on the shelf. And it had enough. The last time this shoreline was at the beach was when it was deposited 22, 23 million years ago.
You beat it. You beat it, buddy. Go.
So what we're looking at here is a core from the Mrs. S.K. East B-51 in Sarita Field in northern part of Kennedy County, Texas. So 3 miles down, and we're looking at a shore face, a Frio shore face. The bottom of the core is over here to your right, and it starts at 14,281 and it goes up to 14,222, I believe. Is that what's at the top? 222. Now,
with the charger, what about
okay, so anyway, for that distraction, we're getting high frequency sea level changes, and we are getting complete inundation. Now, the thought is that could be the infill of a swale. That's a really good thought as we get up into the high section. But at around 48 or 50, we now start to see the bed set start to coarsen upward. So now we're into real shoreline program. Any questions about this? We can linger for a few minutes. I've got a few beers left. This was full of gas. I don't know what this. I think this well made 6 or 8 BCF out of the sun. So this was it's on the order of less than 10 millidarcies in some places, maybe a little bit higher in others. But it's pretty tight sand, tight gas sand. When we look at this core, we're going to see a lot of interesting things. Basically, you start out in what would be water depths of 100 feet offshore. And that interpretation is based upon 2 things. One, what you see are fining upward bed sets. Bauma turbidite beds. Bauma AB and a little bit of C, all fining upward. And they're interbedded with marine shales with horizontal burrowing and some bioturbation. So we would interpret that, I would interpret those to be storm events. In some places those could develop into hummocky beds and represent offshore, deeper water, not foreshore and onshore deposition. But as we work our way up, we come out of these storm beds into more shelfal type shale deposition, heavily bioturbated. You see good horizontal burrowing. And then you work your way up, and then at about 58, 57, you get another event bed. Now this event bed is also fining upward, but it's a much thicker bed set. So maybe one might think that you're starting to get into the toe of some prograding shoreline system. And then as you go up and up and up, you see thinner high stand shales, but they're still high stand shales. Because remember, sea level doesn't go up, it goes up at very high frequencies. I usually ask my geology students, I'll say, what is the highest frequency of sea level change? And they'll usually think and look at me and they'll say, tides. And I'll go, well, there are ripples on top of tides. You know, there are waves. There are ripples on waves. You know, so sea level change never occurs like this. It's always these higher, super high frequency events.
Make sure they're...
This was fracked.